In this video, we're going to learn how to find the derivatives of the sine and cosine functions using the definition of the derivative. And so the definition of a derivative is always the limit as h goes to 0 of the function of x plus h minus the function of x divided by h, so that I calculate the change in the function divided by the change in x. And I do that as a limit as that change in x, h, goes to 0. So here I have the derivatives of the sine and the cosine function. And all of the properties of calculus are going to be consequences of the identities for the sine and the cosine. And so I want to remind you of a previous example where we saw something similar, the derivative of the exponential. When we looked at the exponential function and calculated its derivative, we defined the derivative in the same way, the function at x plus h minus the function at x divided by the change in x, or the h. And so if I were to go through and calculate these, it's always in terms of here the base e, so let's rewrite this. This is equal to the limit as h goes to 0 of e to the x plus h power minus e to the x all over h. And what I do is I use the properties, the identity of exponentials, to rewrite that as a limit as h goes to 0, e to the x, e to the h minus e to the x all over h. And so what I've done is I've made a transformation from the exponential of a sum into the product of two exponentials. Once I have this, I can factor out my e to the x, so that I can write this is really the limit as h goes to 0, factor out e to the x, and I'm left with e to the h minus 1 over h. And what happens is this e to the h minus 1 over h as h goes to 0 is this famous limit that we developed where we said there's a special number e that has this property. And e is the only base that when you take the base to the x power minus 1 over x and let that x go to 0, you get the number 1. So this limit is e to the x times 1, or just e to the x. And every other base there was a logarithm factor. So we found the derivative, and we did it, and the key step was using this identity. What we'll do now is we'll do that same idea for our trig functions. So going back to our derivatives of our trig functions, we need to expand the sine of x plus h. And we'll do that using our trig identity, the sum identity. So we get the limit as h goes to 0. Our sine of x plus h gets expanded as sine cosine, sine of x, cosine of h. So sine cosine plus cosine sine, so cosine x, sine of h. That's our sum identity, minus the original sine of x that's in the numerator. And we get to divide this by h. And so what we've done is we've expanded using the trig identity sine of x plus h. What I'm going to do now is I'm going to recognize that I've got some common factors. Sine of x appears twice, and so I'm going to group those and rewrite my limit. So I have a limit as h goes to 0. Let's factor out that sine of x from the two terms that it belongs to. Cosine of h from the first term minus 1 from the second term, plus cosine of x sine of h over h. And what I want to recognize now is that these factors, sine of x and cosine of x, actually don't depend on h at all. They're constants. And so I'm going to rewrite my limit as the sum of two limits with these factored out. So I get the limit as h goes to I wanted to write that as factored out the sine of x times the limit as h goes to 0 of cosine h minus 1 over h. And then I get to add a second term where I factor the cosine out times the limit of sine. I'm going to run out of space. Let me fix that. Plus the cosine times the limit of sine of h over h. So I've factored out the parts that don't depend on x. And I have these two limits that I'll need to worry about. So if I do the same thing for the cosine and calculate its expansion, I do a similar thing. I rewrite my cosine of a sum as cosine, so cosine x, cosine h, minus sine, so minus sine x, sine h. That's the expansion minus cosine of x. Divide all of this by h. And again, I'm going to look for common factors. So I can factor out my cosine. It appears twice. And then I have a constant sine that's not changing with h. So that I can write this limit as the cosine of x times the limit as h goes to 0 of cosine of h from the first term, from this cosine of h, minus 1, which is really coming from my second cosine of x, all over h. And then I get minus, because of the identity for the cosine sum identity, minus sine of x, limit as h goes to 0 of sine of h over h. And again, I have those same two limits. I need to know the limits of sine h over h and the limit of cosine h minus 1 over h. One of the limits that we needed to find, the limit of sine x over x as x goes to 0, we actually did earlier. And we did that for any angle, but we found that only if we measure our angles in radians do I get the number 1. If I get degrees, we get some sort of factor like 2 pi over 360. So we get different answers if we use different measurements. We want to get a number 1, and we get that by measuring all of our angles in radians. But we haven't ever calculated this formula for the cosine. And one of the things that's useful to notice is that we're actually calculating the slope of these functions at 0. We can get a little bit of intuition if we think about our unit circle. So let's draw a quick unit circle here. If I am at 0, my angle is at 0, notice that my cosine is at a maximum. And the slope at a maximum has to be 0. So by this idea, we expect that this limit is 0. This is what we expect. But we want to actually see why this is true. And I'm going to show you using a trick called multiplication by a conjugate. You see, there's a relationship between sine and cosine. Sine squared plus cosine squared is always equal to 1. That's the Pythagorean identity. And so notice what this says. It says that if I subtract 1 cosine squared of x and I subtract 1, that I'll get negative sine squared of x. And this cosine squared of x minus 1 factors. I get cosine of x minus 1 times cosine of x plus 1. And one of these factors is the formula we have, cosine x minus 1. So what we'll do is we're going to multiply top and bottom by the cosine of x plus 1. That's the conjugate. So cosine's derivative at 0 is the limit as h goes to 0 of cosine of x minus 1 times the cosine of x plus 1 divided by x, and we have to have the conjugate in the denominator as well, so that when I multiply out the numerator, I'm going to be replacing that with minus sine of x squared. So this is the limit as x goes to 0 of minus sine of x squared, so that's times sine of x, over x times the cosine of x plus 1. Now we know that the limit of sine of x over x as x goes to 0 is 1. Because we are continuous, sine of x goes to sine of 0, which is 0. And the cosine of x goes to cosine of 1. Sorry, cosine of 0, which is 1 plus 1, or 2. And so this fraction converges to negative 1 times 0 over 2, which has a value of 0. And so we found the limit of the cosine. We verified that cosine's derivative at 0 is 0. We are, in fact, at a maximum. Well, now that we know these limits, we can finish our calculation. We have learned that as h goes to 0, cosine of h minus 1 over h, the limit of that fraction is 0. And we've learned that the limit as h goes to 0 of sine of h over h, this limit is 1. And so the derivative of the sine is the sine of x times 0 plus the cosine of x times 1. In other words, the sine's derivative equals cosine of x. If you take a derivative of a sine, you get a cosine. The same idea. The cosine of h minus 1 over h as h goes to 0 is 0. The sine of h over h as h goes to 0 is 1. So the cosine's derivative is cosine of x times 0 minus the sine of x times 1. Or in other words, minus sine of x. This is the derivative of the cosine. So when you take a derivative of a cosine, you get negative sine of x. And when you take the derivative of the sine of x, you get the cosine of x. And now that we know these derivatives, we can start using calculus. We can use calculus rules to find derivatives of functions involving sine and cosine.